So, as I was mentioning last time, nature is going to, when we talk about metabolism, or really catabolism, that's breaking molecules down into simpler and simpler products that we can extract energy-rich molecules from. Nature can do this with both lipids, carbohydrates, and proteins. We talked about how carbohydrates, through a process called glycolysis, get converted into pyruvate. And we will see that then two of the carbons from pyruvate end up in acetyl-CoA, and one of the carbons from pyruvate ends up as CO2. Acetyl-CoA is a key intermediate because we're going to see that products from protein metabolism become, in many cases, a lot of acetyl-CoA, and products from lipid metabolism become acetyl-CoA. Then nature takes acetyl-CoA and runs it through the citric acid cycle. That generates another set of two molecules of CO2 for every molecule of, we won't worry about balancing the equation here, for every molecule of acetyl-CoA. You also get out NADH and a molecule called FADH2. Those are electron-rich molecules, which can then go to the electron transport chain in mitochondria, drive the formation of a proton gradient across the mitochondrial membrane, which then feeds the ATP synthase and allows ATP to be synthesized, which then drives a lot of biological processes, including thinking and moving around and a lot of different things. We won't spend a lot of time talking about protein metabolism. You have various enzymes called proteases, and there are many of these that can break down proteins into their component amino acids. And then for a lot of the amino acids, there's a process called, unsurprisingly, amino acid metabolism, whereby you can convert amino acids into acetyl-CoA or into portions of the citric acid cycle and thereby extract energy from there as well. Overall, the process, though, oxidizes the carbons in glucose all the way up to CO2, and we'll see that process. It's quite complicated. It's not easy, but it's controlled and it works quite quickly. The other thing to be aware of, I said we won't talk about amino acid metabolism. You've learned about proteolysis. I showed you the mechanism of how a serine protease breaks an amide bond, and that's where we will leave it. We're going to use a similar class of enzyme called a lipase, which is going to break the lipid apart into two pieces. One is going to be glycerol. Drawing it wrong. Glycerol is the 3-carbon alcohol, which we're going to see can be modified and go into some of the glycolysis pathways. So I'll show you where glycerol intersects with glycolysis a little bit later. The other thing is that for each triglyceride that we metabolize, we end up with 3 fatty acids, and there's a process called fatty acid beta oxidation, whereby fatty acids are converted 2 carbons by 2 carbons into small acetyl-CoA chunks, and then those go through the citric acid cycle. So what we'll spend our time on for the next couple of days is the lipid metabolic pathway, fatty acid beta oxidation, then we'll start in on glucose, glycolysis to pyruvate, and then we'll go through to the citric acid cycle. And when we're done, you'll have a good feel for all of the intermediates along the way, what the correct arrows are, and at least for some of these reactions, you'll know the enzyme names and what the enzymes are doing. All right? So let's dive in. First, where it comes to lipid hydrolysis of these esters, I'm going to refer you back. The text doesn't have this, but I'm going to refer you to the mechanism of serine proteases hydrolyzing amide bonds. It's essentially the same catalytic triad, so just as serine proteases catalyze the hydrolysis of amides, so lipases catalyze the hydrolysis of esters. We won't talk about that mechanism in detail because you've seen it before and it's in your text in chapter 23. So you can go back to your chapter 23 notes on the catalytic triad and see how that's done. I want you to understand that, but we're not going to repeat it here. Let's now talk about what happens to glycerol. And the idea here is that glycerol is a 3-carbon alcohol, but the molecule that the molecule that we want to use in glycolysis is actually also 3 carbons, but one of the oxygens, the one in the middle, has been oxidized to a ketone, and then one of the outside oxygens is actually the phosphoester. I will draw that out for you, draw the Lewis structure out for you. This phosphate group, I'm going to draw it with 2 negative charges. The pKa of the corresponding conjugate acid with 1 negative charge and 1 proton is around 7. So at physiological pH, it is totally reasonable to draw this particular phosphate group either as the monoanion or the dianion. I'm going to just draw it as the dianion to be simple and to be consistent with what is in your text. So this molecule over all the way on the right is called dihydroxyacetone phosphate. And it is one of the substrates or intermediates in glycolysis. And so if we can convert glycerol into dihydroxyacetone phosphate, why then we can shunt that into glycolysis and move on from there. Okay, so the first reaction is a kinase reaction. The enzyme that catalyzes this reaction is called glycerol kinase. Kinase is the name for any enzyme that uses ATP and transfers a phosphate group. So you're going to hear that name all over the time in biochemistry. And it will be helpful to you if you're not, what's a kinase, when you hear it. So here you are. It's a molecule that uses ATP to transfer a phosphate group. I'm going to just represent this in the way that a lot of biochemistry texts might, with arrows intersecting arrows, meaning ATP is used by glycerol kinase to phosphorylate one of the OH groups on glycerol. And the product is glycerol 3-phosphate, which is going to look exactly the same as glycerol, only the 3-hydroxy group is going to have a phosphate on it. Okay, so that's glycerol 3-phosphate. Now, I think you've seen kinase reactions before, so presumably this is not a huge revelation to you, but I'll show you an example of a kinase reaction. For our purposes in drawing the mechanism, hopefully it's okay if I represent glycerol as ROH. You can live with that, I think. For the purposes of a lot of enzyme catalyzed reactions, it is not very clear whether we must remove the proton first or whether we must remove the proton during what happens next. I'm going to just show you removing the proton first to get the alkoxide. I will show you an alternative to that once we've finished with this mechanism. For the next step, we need to draw ATP. I looked it up, or at least have it in my notes now, so I know now that the ATP, the phosphate of ATP that's furthest out is the gamma phosphate group. How about that? If you learn that it's different, feel free to correct me. So here's the triphosphate of ATP. Probably worth a little bit of practice since you're new on your nucleotide structure, drawing this out, making sure you can get it. So there's the adenine base. This is adenosine triphosphate. And understand that in a lot of enzymes that are kinases, magnesium metal, a divalent cation, meaning a +2 charge, is an important cofactor. Likely what the magnesium is doing is associating with the negative charges on the phosphate portion of ATP, perhaps allowing what's over here to be a better leaving group. Because what we're going to see is the negatively charged oxygen attacks the gamma phosphate. We're going to get a pentavalent intermediate, which is going to look like this. And in the future, for future kinase reactions, I may refer you back to this mechanism. We're not always going to draw the arrows because a lot of these kinase type reactions follow a similar pattern. So it's important to get it now. The pentavalent intermediate looks like this. There are 3 negatively charged oxygens on it. We've made the new bond between the 3-hydroxy group of glycerol is right here. And then what's over here is just the remainder of the ATP molecule. And at this stage, since we're tired, we'll continue to draw the sugar, but we can put A here, and that's all right. A is for all right. So, yeah, it's not even worth a groan. All of this is, nope, I wanted it to be gray. There we go. All of this is going to be, well, highlighted in green, is going to be a leaving group. It's going to leave as ADP now because we've gotten rid of one of the phosphate groups. So this is going to be the ADP leaving group. Again, we probably have divalent magnesium metal interacting with the negative charges on those oxygens. Electrons will kick down, reestablish an oxygen phosphorus pi bond, and the leaving group will leave, and that will get us to that product. Okay, that is the mechanism for a kinase phosphate transfer. Questions about that? You can think of it as basically very analogous to nucleophilic acyl substitution of carbonyls, only the thing that's getting attacked is a phosphorus rather than a carbonyl carbon. Now I told you I would, yes, go ahead.
When we're like replicating DNA and RNA, it attacks the alpha phosphate, whereas with this one it attacks the gamma.
Right. Why, when we're replicating DNA and in some other cases, do we attack the alpha phosphate versus the gamma phosphorus? I don't know. They're similar in reactivity, so it's got to be enzyme control. Think of how the enzyme might do that. One of the ways enzymes work that you'll learn about in 481 is that enzymes stabilize transition states and or intermediates. So look at this intermediate with a negatively charged phosphorus. If you had groups nearby that could hydrogen bond with those oxygens, that might stabilize that intermediate or that transition state and make the reaction happen faster. So you could imagine that an enzyme that's supposed to direct attack on the gamma phosphorus might position its hydrogen bond donors over here, whereas an enzyme that's going to direct alpha phosphorus attack would position them over here. So that may be an enzyme issue. Yep, okay. I said I would show you one alternative to dealing with deprotonating the OH group from glycerol. Some of you will like this, others will not. As I said, sometimes it's not clear in enzyme mechanisms whether you must first remove the proton and then attack happens. That's called specific acid catalysis, or whether you must remove the proton while attack is happening. That's sometimes called specific general acid or general base catalysis. So here, a base removes the proton at the same time as the oxygen is attacking. If you wanted to, if you hated that and you wanted to do something different, you could use even more arrows to show breaking of the pi bond with a different lone pair, but we don't really have any way of labeling electrons, so we just don't know. Either of those options are okay. Sometimes it's known that you must deprotonate first. Other times it appears that it's known that you must deprotonate while. We're not going to die on that particular hill. Yes?
Just to make sure I understood, specific protein catalysis is kind of one step where you just deprotonate, and then general proton catalysis is just one step faster.
Yeah, it's a little bit more complicated than that, but that's a decent way of summarizing it for this class. Specific base catalysis is where you remove the proton first and then the slow step happens. General base catalysis is where you remove the proton during the slow step at the same time. Yeah. I'm not going to ask you about the difference between that, but those terms will show up in 481. Yeah.
On the dihydroxy acetone phosphate, how is the ketone formed?
Yep, we're not done yet. We're missing a step. Yeah, we've only gotten, the question is, how do I get the ketone? You got glycerol 3-phosphate. Clearly that secondary OH group's got to get oxidized, so that's the next step. Others? Okay, so let's do that next step with glycerol 3-phosphate. And then the product is dihydroxyacetone phosphate. It's an oxidation reaction. And of course, if we were in the lab, secondary alcohol to ketone, I would want to use some oxidizing agent like CrO3 or PCC, though I would worry about not oxidizing the primary alcohol. This is where the enzyme comes in. The enzyme can activate one of these two for oxidation and leave the other one alone. So the enzyme that does this is called, often enzymes are named for their substrate, meaning the starting material, glycerol 3-phosphate, and then they're also named for what they do, dehydrogenase. There are a lot of ways to name enzymes that are involved in oxidation and reduction reactions, but in particular, the term dehydrogenase is a signal that this is an enzyme that's involved in redox reactions, meaning something's going to get oxidized and something's going to get reduced. In this particular case, we're going to use one of nature's oxidizing reagents, which is called NAD+. You've maybe seen NAD+ before, but I think you probably haven't seen it used as a reagent. You've seen it as a product in a reaction of a reduction reaction. NADH is the reduced form of NAD+. So in this direction, as we go from left to right, glycerol 3-phosphate is going to get oxidized to dihydroxyacetone phosphate, and NAD+ is going to get reduced to NADH. Okay, so let's get a refresher on the structure of NADH. This is going to appear all over the place in our in glycolysis. The structure of NADH is actually pretty decently complicated. I will draw it out for you once, and then I will show you how we're going to abbreviate it, and we'll just go from there. So, and friends, there are some problems with the structures. No, actually, it's fine. there's some problem. There's not a problem with the structure, but there's a problem with a mechanistic arrow that appears in section 27.2 of your text about NAD+, which I will correct now. All right, so here is the NAD+ is based on sort of a nucleotide type structure. In fact, the D in NAD stands for dinucleotide. The business end of the molecule is right here. It's an N-glycoside, but instead of having a typical base on it, it has the following structure. Oh, and I'm afraid I'm going to get it wrong, and I don't want to. So, oops. So the N-glycoside in NAD+ is this pyridinium ring, a positively charged nitrogen in a benzene ring. There's an amide bond at this sort of meta position relative to the nitrogen. And in a second, I will convince you that this carbon here is electron poor. While we're drawing the rest of the molecule, think on that and see if you can convince yourself why it's electron poor. Then you've got the 5' hydroxyl group, which is itself bonded to 2 phosphates. And then the second phosphate is itself bonded to another 5' hydroxyl group of another ribose unit. And then this is the adenine base, which I will just abbreviate with A. So this is NAD+, and that stands for nicotinamide. It is related to nicotine, nicotinamide adenine dinucleotide. This portion here is the adenine portion, this portion here is the nicotinamide portion, and this is the dinucleotide portion. That's NAD+. Now, fortunately, the only thing we really need for the arrows is the nicotinamide portion. So for the most part, I'm going to use either a squiggly line or an R group here whenever I draw a mechanism for NAD+. Okay? Now, back to that issue. Why is that carbon electron poor? Any ideas? Somebody's saying the magic word resonance. Now tell me, do you really believe that, or are you just saying words that you know are frequently answers? Matthew, go ahead. Say what? It's not an alpha carbon, but it is beta to what? Carbonyl. And carbonyls are electron withdrawing. So you should be able to see that I could draw a resonance structure that would look like this. That would have a positive charge on this carbon, a negative charge on the amide oxygen, like that. Is that sort of what you're envisioning? Did I do something wrong? I heard muttering and I got self-conscious, because often when you guys are muttering at me, it's because I've made a mistake. So the other way you can see this is to move the pi bonds around in the nicotinamide ring. If we move this pi bond here onto the nitrogen as a lone pair, and this pi bond here to form a new pi bond there, then there's your amide group. So we've identified 2 resonance structures where that carbon that's sort of para to the nitrogen is electron poor. And so NAD+ is a good electrophile, and that carbon is a good acceptor of electrons, or a good acceptor of a nucleophile. So let me show you what's going to happen in this mechanism. Here I'm going to draw glycerol 3-phosphate. I'm going to draw the OH of glycerol and then also the hydrogen on that secondary carbon. Okay? It's thought that what happens, and again, the proton transfer steps, we're going to be, you can sometimes worry about whether they happen separately or in the same concerted step. We're going to just be ambiguous about that. It's not a hill that we want to die on. A base removes the proton. You could draw the resulting alkoxide in a separate step, or you could show the electrons from that oxygen-hydrogen bond kicking down immediately to form a new pi bond, and then H- leaving. Now, people historically have a hard time accepting this because they're used to thinking of H- as a terrible leaving group, and it is. We've never seen H- on its own floating around in solution. It just doesn't happen in organic solvent. It also doesn't happen in biology. What instead is happening here is that the NAD, the nicotinamide portion of NAD+, is so close to the glycerol 3-phosphate molecule that the glycerol 3-phosphate molecule is literally handing the hydride off directly. H- does not float around in solution. It does not say hello to the enzyme active site. It does not shake hands with the water molecule. There's no chance for it to even exist on its own. It's immediately handed off. And so we will show that with the following arrow as the negative, as the hydride from as that H- is leaving, it's handed off directly to the electron deficient carbon of NAD+. Then we'll need a few more arrows to finish the process. These pi electrons come here and these come here onto the nitrogen. Of course, you should be able to see how you could draw this same mechanism from either of these resonance structures to end up with an equivalent alternative. But in the end, we've made the ketone oxidizing, and we have reduced, so the ketone is now oxidized. This is dihydroxyacetone phosphate. And then what we have over here is now NADH, where the added H reflects the fact that we got an H- from our starting material, glycerol 3-phosphate, and we reduced NAD+ to this reduced form. And I need to erase the night. There we go. Okay, so this is the reduced form NADH. Yes?
Does that take a lot of energy since we lose the aromaticity?
Great question. Does that take a lot of energy since we lose aromaticity? And this is a clue to what's going on with NAD+ versus NADH and why they are so useful as redox reagents. We noted, I didn't point out, but I told you previously that NAD+ is electron deficient, but it's aromatic, right? Fully conjugated ring. It's just permanently positively charged. NADH is no longer electron poor, it's electron rich, but it's no longer aromatic. This trade-off between electron poor, aromatic versus electron rich, but not aromatic, is why NADH is good at accepting hydrogen, why NAD+ is good at accepting H-, but it's also why NADH is good at donating H- in reduction reactions. So, and this gets to an issue of something called redox potential that you may have learned about in general chemistry. My guess is you don't want to revisit those horrible days, and so we won't, but they weren't horrible, they were just challenging in a different way. Okay, so yeah, that is an important point, that you lose aromaticity when going from NADH to NAD+ to NADH, but you gain, you resolve your electron poor problem. Okay, what else? All right, good. So one other thing, I will point out actually that sometimes biochemistry texts, when they're showing this type of oxidation reaction, they will put comma, proton. What the heck are they doing there? First of all, there is no such thing as a proton on its own. It's always bonded to something, perhaps a water molecule. All they mean about that is that the process of reduction requires an acid-base step where you remove a proton. I detest writing it that way, so I will not. You will see it almost all the time in biochemistry. Understand that that proton that's sitting there is the one that they took off the alcohol so that they could do the reduction, do the oxidation reaction. Okay? Yes?
Maybe this isn't relevant, but why on NADH is there the whole ADP part of it? Like why?
Yeah, what is the rest of this doing? And you could imagine this, if you looked at a crystal structure of an enzyme bound to NADH, ready to do a reaction, you would see that all of this is bound. So you can think of this as the handle. Why does a scalpel need a handle? So you don't cut yourself while you're going in there to cut somebody else, I guess. In the same way, the enzyme probably uses all of this to position this group in the right place. Yep. All right, good. So with that, then dihydroxyacetone phosphate goes to glycolysis. NADH can be used for reduction reactions in synthesis, or it can be used to deliver electrons to the electron transport chain. And it's thought that you can get anywhere from 2 to 3, I think, molecules of ATP per NADH, given what we know about the electron transport chain. So ultimately, an NADH molecule can lead to the production of ATP. So anytime you see NADH in a process, you think, yay, that's energetic payoff. We can do something with that. I'm still alive. And when you're breathing, you're using electrons delivered to your electron transport chain from NADH to reduce the oxygen you inhale from molecular oxygen to water. Okay, so now what happens to the fatty acid? This is the process called beta oxidation, and it's interesting because it's iterative. As you know, fatty acids sometimes have 18 to 20 different carbons in the chain, and the process that we're going to learn is 4 steps. Is it 4 steps? 6 steps, something like that. I should probably know that, shouldn't I? The process that we're going to learn will repeat again and again and again to break the fatty acid into smaller parts. And the beauty of it is that each individual step is something that's pretty straightforward to understand based on things that you already know, reactions that you've learned. So, fatty acid beta oxidation. You will see very soon why we call it beta oxidation. I'm going to draw a fatty acid. We're going to let an R group be everything but the last few carbons. And let's see, we need to begin with carbon alpha beta 2, that's fine. Okay, so we've drawn 4 carbons of our fatty acid. Step 1 is going to be conversion of the fatty acid, activation of the fatty acid first to the carboxylate acyl AMP, and then to the thioester. Okay, so the first mechanism is a kinase-like mechanism. You will use, and you've seen this kind of reaction before when we did nucleophilic acyl substitution. So this is going to be mostly a review. This is going to be a kinase reaction which has the carboxylic acid, the carboxylate rather, act as a nucleophile to attack one of the phosphoruses of AMP, only this time it's going to be the alpha phosphorus instead of the gamma phosphorus. So we'll show lone pairs on the carboxylate oxygen attacking the alpha phosphorus. I don't like that arrow, so I'm redrawing it again. It didn't turn out much better than it was, oh well. Okay, that mechanism is going to involve an intermediate very similar to the one we saw previously in a kinase reaction, so I'm not going to repeat that mechanism here. Presumably you can draw the pentavalent intermediate where the phosphorus is attached to 5 different things. Then electrons kick down and the leaving group leaves. When we're done, we now have a new bond between oxygen and phosphorus. That phosphorus is the former alpha phosphorus. It's attached to the 5' hydroxyl of the adenosine ribose ring. And this is called a fatty acyl AMP. And then, of course, the leaving group in all of this is what's here. That's pyrophosphate. It's probably bound to magnesium before it leaves and even after it leaves. And then that pyrophosphate later on can go on to be hydrolyzed by water to 2 individual phosphate ions. And I can't spell pyrophosphate again. I still remember screwing that up in a previous lecture, which provides a driving force for the reaction, okay? So this first step is activation of the carboxylate as the fatty acyl AMP. And you can see the difference. We went from something that used to be a nucleophile, and then we used ATP. And now, instead of being a nucleophile, you've got the carboxylic acid attached to something that could conceivably be a leaving group. This portion of the molecule would be called AMP, and it's a potential leaving group. So we've converted our carboxylic acid from a nucleophile to something that is ready for nucleophilic acyl substitution. Okay, questions about that? I think you've seen that before. The next step is going to be to start with this fatty acyl AMP, which I'm just going to abbreviate like this. We're going to use coenzyme A as the nucleophile. And then in the end, we're going to get a thioester out, and then we'll get AMP, adenosine monophosphate, as the leaving group. Okay. The mechanism here, actually, I think you've done something similar to this before on an exam. The mechanism here is nucleophilic, and I can't spell, acyl substitution. I would expect you to be able to draw that mechanism if I asked for it. It's really not hard. A base would need to remove this proton. Then the negatively charged thiolate would attack the carbonyl carbon to give you a tetrahedral intermediate. Electrons would then kick down in the next step and kick off AMP as the leaving group. All of that you should be able to draw. I've sort of sketched it out here. If you want to test yourself on your ability to do that, by all means, go ahead and do it. I think it would be useful. So that's sort of the prep for fatty acid beta oxidation. That's the activation step. You have to do this once. So some people might not include these steps 1 and 2 in fatty acid beta oxidation because you have to do this once per fatty acid, and everything we do next will happen on the same thioester. What I want to point out too while we're on the subject is, if you remember way back to the very beginning of class, we ranked stability of carbonyl compounds. We said that carboxylates were very stable and they're not electrophiles. In fact, they're nucleophiles. We said aldehydes, ketones are very, very high in reactivity, kind of at the same level as anhydrides and thioesters. Then we said below that somewhere were esters, below that were amides. Notice that in order to convert the carboxylate nucleophile to this kind of fatty acyl AMP, which is called a mixed phosphoanhydride, notice we had to consume an energy-rich molecule of ATP. In other words, we traded a weak phosphoanhydride bond in ATP for another weak mixed phosphoanhydride bond in the fatty acyl AMP. You had to lose ATP to get there. Why? Because the carboxylate itself is not that reactive. Notice, though, that having that mixed phosphoanhydride bond and the good leaving group in place, it's no trouble at all to swap out one good leaving group for another, to exchange from mixed phosphoanhydride to thioester. And you'll see these kinds of patterns as we go along and look at metabolic reactions. Okay, so what we'll do now for fatty acid beta oxidation, and maybe I'll restart here with step 1, repeats, and you only need one fatty acid to get the process started. Again, I'm going to draw a couple of carbons in the fatty acyl thioester. The first step is an oxidation step. The enzyme that catalyzes it is called acyl-CoA dehydrogenase. So that tells you this is a redox step. The product is going to be one in which we now have a double bond between the alpha and the beta carbons. So before, in the fatty acid, notice that the bond between the alpha and the beta carbons is a sigma bond, and both of those carbons are fully saturated with hydrogens. Notice that after the reaction, there's going to be unsaturation. That is, we will have lost hydrogen atoms from both the alpha and the beta carbons. And the fact that we're going from an alkane to an alkene tells you that this is an oxidation reaction. This molecule is oxidized. In order for an oxidation reaction to happen, you need an oxidizing reagent. In this case, it's not NAD+, it's a molecule called FAD. And FAD functions much like NAD+, but has slightly different structure and slightly different properties. But it gets reduced to form FADH2. And that's where the two hydrogens go, one from the alpha carbon, one from the beta carbon, and they both end up there. Okay? So FAD is also analogous to NAD+, though it's got some different structural issues which your text shows you and which I will show you now. Interestingly, FAD has exactly the same structure as NAD+, only the N-glycoside is different. So I'm not going to redraw all of FADH2 for you. I'm not going to draw the adenine portion and the phosphate bridge, or even this ribose ring. I'm just going to put an R group on it, but you're going to have to remember that that R group is all of this. All right, so let me draw the abbreviated form of FAD, and then I'll show you how it functions as an oxidizing agent. Here's the nitrogen that's attached to the ribose ring of FAD. That nitrogen is involved in a 6-membered ring, but at the para position is another nitrogen. All right. We're not done yet because there's more. And there's actually a lot more. Carbonyl here, carbonyl there, a proton there, a double bond there, and a double bond there. At this point, you probably want it to be done, but we are not done because there is another 6-membered ring on the other side. With 2 methyl groups. This portion of the molecule, that N-glycoside, is called flavin. And that's why this is called flavin adenine dinucleotide. Okay? Now, it's not as immediately apparent looking at flavin as it was for nicotinamide why this is a good oxidizing agent. You would expect it to be electron poor, and it is, but it's not immediately obvious. And to see that it's electron poor, you would need to notice that this nitrogen is conjugated with that carbonyl oxygen. I'm just going to briefly point that out by erasing some pi bonds. I'm going to undo it, so look real quickly, but we could put all the lone pairs on this oxygen, the pi bonds there, and a positive charge on that nitrogen. Now that's not the best resonance structure, but it illustrates that that nitrogen is electron poor. So I want you to end by, if you remember the structure of NAD+, it's the para position relative to the N-glycoside nitrogen that's electron poor, and that's exactly the same here. So maybe by analogy you can remember that. What happens in this oxidation reaction is exactly what you would expect. I'm going to copy the structure of the acyl-CoA. Before H- can get kicked off this molecule, we need to remove a proton. Of your available protons, which should be more acidic, the ones on the alpha carbon or the ones on the beta carbon? Alpha, right? We're used to that. Hello, everything you did about enolate chemistry. So our first step in this mechanism is remove the alpha proton to make the enolate. Okay, so now we've got the enolate. The alpha proton, alpha carbon is negatively charged. Now what's going to happen is an E1CB style elimination. E1CB means we make the leaving group first. The leaving group, we make the enolate first. The leaving group is going to be one of those 2 hydrogens with its electrons. And electrons from the negatively charged alpha carbon are going to kick down and remove the hydride. Now, again, just as with the NAD+ mechanism, hydride is not floating around in solution saying hello to everybody. It's not stable. It's handed off directly to FAD, and the only reason it can leave is because it's handed off directly to FAD. It's going to go to that electron-poor nitrogen. What happens next is necessary to not break the octet rule. You have to move this double bond here, and then this double bond could move out onto the nitrogen. It could also move to form a pi bond here. Instead, what your text shows is that picking up a proton from solvent or some group in the enzyme active site. Okay, that's all we have time for today. We'll pick up there next time.